Okay, let's get started. All right, so let's review what we covered in our last lecture. So in our last lecture, why it move automatically? In our last lecture, we finished talking about relative entropy, and then so we apply what we learned before, and then we talk a little bit on more on the chain rules, right? So we introduce the chain rule on relative entropy and also on the mutual information, right? And then we talk more on the mutual information, right? We introduce you the concept of conditional mutual information. All right, so first we introduced the conditional relative entropy, okay? So I write that in this way. I think that is more clear, but in the book, probably it does not have this condition part, right? But just make sure, notation might be slightly different, but we're talking about the same thing here, okay? All right, and and then we introduce you the chain rule for relative entropy, right? So it's given by this, right? So this equals to the relative entropy between P and Q, and also the relative entropy between Px given Y and Qx given Y and given P, okay, given Py, okay? So I think it's relatively easy to remember it. And then, so we introduce you how to write mutual information as a function of relative entropy, right? And how to write mutual information as a difference between the relative entropies, okay? So for each of them, you may have some different understanding for mutual information. For example, for this Y, so it means that given X, right? And then, so what is mismatch between Y given X and Py, okay? And in this case, so basically, so this is a difference. This is a difference between two mismatches, right? So one mismatch is that given X, then what is mismatch between Py given X and Qy, and here what is the mismatch between Py and Qy, okay? So here we introduce another quantity or another PMF Qy here, okay? So here you may imagine that, okay, if we know X, right, and Qy is some kind of estimation, right, for example, right, if we know something, right, then the mismatch between Py given X and Qy can be bigger than the mismatch between Py and Qy without knowing X, right? And the difference between these two will give you the mutual information. Okay, hopefully that makes some sense to you, but right. And then we talk about the chain rule for mutual information, right? So that's given by this formula, right? To prove that it's relatively easy, we can just use the chain rule for entropy to prove that, right? And also, we can use other property to prove that as well. So, I think from now on, it's very important to remember this formula. Okay, so we're going to use it again and again. So chain rule is probably one of the most important property for information theory. Later on, you're going to see why is that, right? So maybe just give you a head up. So this x power n, so it's a vector of x, right, with a length n. Okay, so that's very important in information theory, right? For example, let's say, so we're talking about coding, right? When we talk about coding, so we never only code one symbol, okay? So we code them together. So that can save something. So we're gonna see that later, right? It basically means that we're always talking about, a sequence of x, okay? Therefore, we always use this kind of relationship in our class, okay? So that's very important. Right, and then, so we'll give you some example to talk about the conditional mutual information, right? So normally when we, talking about this conditional property, it is pretty weird. Okay, so we need to be very careful. The only thing I think that is pretty clear is the conditional entropy, right? We know condition will reduce entropy, right? Which is easy to understand, right? If we know something, then of course the uncertainty will be reduced, right? If they're related, of course, right? But for mutual information, it's not the case, right? If we given the condition, it could be, the mutual information could either increase or decrease, depends on scenario, right? And we give you one example here to show you that the mutual information actually increase here, okay? And so this scenario is that we consider 3 random variables, x, y, and z, and we consider where x and z are independent, right? So in this case, okay, so the conditional mutual information on z would be increasing. It would be increasing. Okay, why is that? So we'll give you some one kind of proof, right? So give you the one way to prove it in the class, right? Because the mutual information can be written as the entropy, the difference between entropy and the conditional entropy, right? For the first term, let's say it's hx, right? And for the other term here, so it's x given z, right? If z and x are independent, then the first term hx and hx given z are the same, right? But for the latter term, it could be different, right? So yeah, maybe let me see. Yeah, actually, this is kind of important, I think. Let's see. Not this. Yeah, let me share my iPad. Okay, so yeah, in the last lecture, lecture 7, right? So, oh, by the way, there's a typo here. So I forgot the log here. So yeah, just to make sure. Yeah, these are, oh yeah. Yeah, in the last lecture, in the last part, yeah, we can write mutual information as this guy, right? So hx minus hx given x, and then hxy, not h, mutual information between x and y given z. That's equal to this minus that, right? And then we can see for the first term, hx and hx given z, right? We know this term is less than or equal to this term, right? But if x and z are independent, then this term and this term are equal, right? So the first term does not change, then the second term, so we have more condition here, so this would be less than this guy, right? Therefore, this will be bigger than this guy, right? Does that make sense? Okay, so maybe we need to be, intuitively, we need to may want to pay more attention here. So given y and z, right, y, it can reduce entropy, right? We know condition reduce entropy, right? But here, what we are given here compared to this is z. Z and x are independent, right? Y given additional z would reduce entropy in some cases.
Because there's a possible dependence on like y and z. So.
Yeah, y. Yeah, that's totally correct. Yeah, there's a possible dependence on y and z, and then y given z, but x and z are independent, right? So it basically means that y, there's a dependence between y and z can help you to reduce the dependence on x, not dependence, uncertainty on x. Right, in other words, so you may think that x and z are independent, but given y, x and z may not be independent. Does that make sense? Kind of tricky, right? See whether you can have any example on that. Right, you may think for example, let's say x plus y equal to z, and all x, y are like 0 and 1. And this plus means XOR, for example, right? And you'll see that, so clearly, given y, x, and z are independent, given y, x, and z are not independent, and x, z are independent. Does that make sense? Yeah, think about that, right? So this is kind of tricky, but I think this will help you to understand this well. Okay, so in this class, in this class, we're going to continue talking about this. And let's see, today is our lecture number 8. So today we're going to finish talking about conditional mutual information. And then we'll finish, introducing all the information theoretic measures, okay, metric. So, and then we're going to talk about more on the information theoretic inequalities, right? Or 4 important inequalities. The most important one, is the Jensen's inequality. Yeah, probably we're only talking about that. If we have time, we'll talk about log sum inequality as well. But let's see how much we can go for today. Okay, so conditional mutual information, x and y given z. Okay, so the first special case that we covered is that so we consider 3 random variables here, p, x, y, and z. Okay, and now we consider the case where x and z are independent, right? In other words, this basically means the distribution between this and equals to px, pz given x, and py given x and z. So here, just to use the Bayes rules twice, right? So nothing special on that. And if this and this are equal, right? So basically it means x and y are independent, okay? And then, so we can say that this guy is bigger than or equal to this guy, okay? So we show that, you know, by just expand it using 2 ways, right? So now we're going to prove it in another way. So the reason I'm writing this is that this is a very important technique that we use all the time in proofs, okay? So basically what we're going to do is as follows. So since we know the chain rule for mutual information here, right? So we just write the mutual information between x and zy, yz, okay? And then we're going to use the chain rule to expand it in 2 different ways, okay? So the first way is that, you know, there's only like 2 ways to expand it, right? Because we have only like y and z here, right? So we first compute mutual information between x and y, okay? And then plus x and z given y. So this is one way, right? And the other way is we compute mutual information between x and z, and then compute this given z, okay? That's 2 ways, and they're equal, okay? And now it's pretty obvious that because x and z are independent, so this mutual information is 0, right? And clearly, x and y may not be independent, so this mutual information is bigger than or equal to 0. Okay? Therefore, from here, we can conclude that this guy, given z, has a bigger than or equal to and this guy, right? So because this guy is bigger than or equal to 0. Okay, so it's very easy to show that, right? That clear? Okay, very good. So this is basically one example, right? So I think the intuition is very important, right? So when x and z are independent, right, and then, you know, condition can help you, okay? So basically it means that if you know z, you know more about x. So why you know z, you know more about x, because we also condition on y. Okay, we also know y. Okay, that's very important. And the second example is that we want to see when the condition will reduce the mutual information. Okay, special case 2. So can you imagine in what cases, so this can be true, the condition may reduce mutual information? It got to be some cases where x and z are not independent, right? Otherwise, we're following in the other case, right? So now we know, okay, x and z are not independent, right? And x and y are not independent, right? So then, can you imagine, you know, so the structure that condition will reduce the mutual information? Right? Can you came up an example intuitively? Yeah, maybe it's not so easy. Let's see what case that will be and see whether that makes sense or not, right? So basically, in this case, we're considering the this distribution can be written as follows. So it's probability of z given probability of x given z times probability of x y given x and z, right? So now, how about if I write that as, so if this equals to this, okay? So the catch here is that, so given z, this will not help on this, right? These two are equal, right? So if I give you this structure, so does that look familiar? Yeah, who learned or who heard of Markov chain before? Yeah, so yeah, if you're not you have never heard of it, let me introduce you. So basically, if this kind of condition holds, it basically means that x and y and z they form a Markov chain. Okay, Markov chain means follows. Okay, so it's a z. We write that like this. Okay. So basically, the definition of that is basically like this, right? So if, you know, the probability of y given x and z and the probability of y given x are the same, okay? So basically means that given x, then we cannot gain any additional information if we also know z, right? It's kind of a one-step thing, right? So this probability, the transition probability is determined completely by the random variable one step ahead. Does that make sense? Okay, so there's a, yeah, let's see. So yeah, let's talk about that later. So let's say, so this relationship holds if x and y and z follow a Markov chain, form a Markov chain. Okay, so maybe you want to review the concept of Markov chain. You don't need to do that, you know, in a very thorough way, but you need to understand what's the concept of Markov chain. Okay, and in this kind of Markov chain, we have transition probability, right? So here, the transition probability is like px given z and the py given x, right? So those probabilities are important. Okay, so y only depends on the previous random variable here. Okay, yes?
So if x depends on z and y depends on x, how can y not depend on z?
Yeah, y depends on z. It just basically means that, okay, if you know x, and then y and z are not dependent anymore. Does that make sense?
Okay.
Yeah, so x has enough information for z.
Okay.
Okay. Y and z are dependent for sure, but given x, y and z are independent.
Okay, you don't know anything more
Yes.
from knowing x and
Yes,
z. Okay.
something like that. Yeah, so maybe I'll write it down. So basically, it means that, yeah, so given x and y, z, so they are not y and x, right? Z given x, okay, so okay, and because of this, probably you know how to prove it, right? So let's write it down. So if this is a Markov chain, then, so in this case, the mutual information, conditional mutual information, will reduce the mutual information. Okay, it's like if I know that, then the reduction of uncertainty, if I observe x for y, you know, would be less than if I know nothing, and then the reduction in uncertainty. Okay, so that's the fact, right? We can show it. So the proof of that is almost identical as before. So basically, what I do here is that again, so here we write the mutual information of this guy in two ways, right? So one way is a mutual information between y and x, and add the mutual information between y and x given z, and then we write that in another way, y and z, add y and y and wait, yeah, here I wrote something wrong, right? So yeah, here should be y and z given x. Here is y and x given z. Okay, so we write that in two ways, and then we can observe that. So because it's a Markov chain, so given x, y and z are independent, so this guy is 0. Okay, and so this term is what we wait. Which term is what we want? Yeah, this term is what we want, right? So mutual information y and x equal to x and y, right? So this term is what we want, but this term is bigger than or equal to 0, right? Therefore, we can conclude that so this term would be less than or equal to this term, right? And then we can say that this term is less than or equal to this guy. Okay. Yeah, so this proof technique is kind of very important, so just remember that. So any questions? Yeah, so compared to the previous case, one case is that, okay, so two random variables are independent. So here is that given something, given another random variable, then the two random variables are independent, right? Then we have totally different result. Okay, very good. Okay, so now let's do a very brief summary. So now we finished talking about all the information metrics, right? So we have a summary. Okay, so we're basically talking about two types of metrics here. So one type is entropy, and the other type is what? Relative entropy, right? So entropy involves basically one distribution, and the relative entropy involves with more than one distribution. Okay, so we have two families. One is entropy family, and the other one is relative entropy family, or the mutual information, or the K divergence family. Okay, for entropy family, we talk about entropy, joint entropy, and conditional entropy. Okay, and for relative entropy, we talk about the relative entropy and the conditional relative entropy. Conditional relative entropy, and then so we consider a special case which is super important, that is mutual information, right? So we talk about mutual information, and then we talk about the conditional mutual information. So hopefully you have an impression that conditional mutual information and the mutual information can be very different. Okay, so in many works, unless people want to do some kind of application of information theory, purely depends on intuition, right? So if we don't purely depend on intuition, then we need to be super careful on the meaning of conditional mutual information, right? Given something, that can be very different, right? It could reduce mutual information, could increase mutual information, and so on, right? So that is super, super important. Okay. Yeah, my point is that when you see conditional mutual information, you need to have a second thought. You need to be more careful. Okay. Okay. Yeah, let's continue. So now we start talking about the four important inequalities. Okay, and the first one is Jensen's inequality. Okay, in order to talk about Jensen's inequality, we need to first talk about what is convex function. Okay, so yeah, let's introduce what is convex function. Definition of convex function. So we say a function fx is convex over an interval a and b, where a and b are just the real numbers. Okay, so if for every x1 x2, then that is in a and b, right? So this means an open set. Okay, of course x and y, x2 are not equal, right? And then we have a parameter lambda, so that is between 0 and 1. Okay, then the following inequality is true. Okay, we have f lambda x plus 1 minus lambda x2, so that will be less than or equal to. So if we take lambda out, right, so so do a linear combination between these two values of x1 and x2. Okay, so if this inequality holds, then we say the function is convex. Okay, and in addition, we need to see a case where the equality will hold. Okay, so so we say f is strictly convex if the equality only holds if and only if when lambda equals to 0 and lambda equals to 1. Okay, so it basically means that the function, there's no flat point in the function. Okay, and so this is a concept of convex, right? And so we say a function is concave if the negation of that is convex. Okay, we say a function is concave if minus f is convex. Okay, so let's see example. What's the shape of this function if it's convex, right? So probably some of you have know that already, right? So basically, a convex function look like this. Okay, so this is a convex function. Okay, so the meaning of the definition as follows, right? So we take a 2 point here, right? For example, this is point x1, and this is x2, right? So what we need to do is that we compare two quantity, right? One quantity is lambda fx1 plus 1 minus lambda fx2, right? It's a linear combination between fx1 and fx2, right? So here is fx2, and this value is fx1. Okay, so a linear combination between this is that because lambda is between 0 and 1, right? So basically, if we, so this value will take, take all the values on this line. Okay, and if we fix x1 and x2, so probably this value will be here. Okay, so that's the value of this guy. Okay, but if we consider this value f lambda x1 plus 1 minus lambda x2, right? If it's inside, okay, so it basically means that, so we do a linear combination of x1 and x2, right? So there will be some value here. Okay, and the f of that would give you the value here. Okay, so this is this guy. Okay, and clearly in this case, So we have this relationship. Okay, so it basically means that this function is convex. Okay, has to look like this shape. Does that make sense? Let's be clear. So this value is lambda x1 plus 1 minus lambda x2. Okay? So this is the shape of a convex. Okay? It's like parabola, right? Or, and the concave is just something that is opposite. Right? Concave is something like this. Okay, if we do the same thing here, right? So we consider 2 points here, right? And if we do a linear combination inside, say it's here, right? And then the corresponding value would be here, right? And the other value would be here, right? So in this case, so maybe I just don't need to rewrite it. So basically, so this guy is basically this, and this guy is basically this. Okay, and clearly we can see that, so this guy would be less than or equal to that. Okay, so it's the reverse of convex. Right, so in this case, that is concave. Does that make sense? So is the definition clear? Convex and concave. Okay. So why we want to talk about that? Because for most of the information quantity you have seen before, so they are either convex or concave in something. Okay. So we're gonna see that. Okay, and this is very important. So that's a very important property for this information theoretic metric, right? So if we know it's convex or concave, then optimization will become much easier. Okay, because for convex, it's easy to see that we can find the minimum point. Okay, and it's very easy to find it. And if it's concave, then we can find the maximum point very easily, right? So who learned convex optimization before? Nobody? Yeah, who heard of this KKT condition and so on? Oh, nice. Yeah, then where did you hear it? If you
talked about it in the machine learning class.
Oh yeah. Yeah, machine learning, basically, and one understanding for machine learning is view machine learning as optimization, right? Then yeah, you should know most of it. Okay, great. Yeah, we're going to use that in our class as well. So because, as we said, most of the quantity for information theory, they are convex or concave. Okay. So we introduced one theorem here. So basically, it's about how to determine whether a function is convex or concave. Okay. So probably some of you may know that already. So I say if a function f(x) is convex if and only if. So let's say it's a scalar function, right? So if we do the second order derivative, so that will be bigger than or equal to 0, right? If that's true, then the function is convex. Okay, and if the x is a vector, then we have something very similar to that, right? So, but we may not. Yeah, we'll talk about that when we have it. But now we're only talking about the scalar function. Okay, and we say f(x) is strictly convex if and only if this is bigger than or equal to 0. This is bigger than or equal to 0, and the equality only occurs at isolated points. Okay, so strictly convex basically means that, so here there's something flat. Sorry, strict convex means this, right? So not strict convex basically means, this could be flat. Okay, and so I have a lot of minimal points, right? So, yeah. yeah, this is a way to determine whether a function is convex or not, or either is strict or not. Okay, so one example that we use all the time for convex function is fx equal to log x. Okay, so this log could be natural log, right? If it's natural log, we can write that as a ln, right? The reason we use that is derivative is very easy, right? So derivative of this guy is 1 over x, right? And if we do a double derivative of it, it's 1 minus 1 over x squared. Okay, so clearly, so this is less than 0, right? Then we can say that is what? So clearly it's not convex, right? Because it's not bigger than 0, it's less than 0, right? So that's concave. So actually this is strictly concave. Okay, so it means that, it's easy to find its maximum point, right? Of course, under some constraint. Okay. Okay, very good. So yeah, this is the definition of convex and concave, and we're okay with that. And then we can introduce you the Jensen's inequality. Okay, so Jensen's inequality basically means as follows. So we let x be a random variable, okay, and fx be a convex function. Okay, then, so we're going to find what is the relationship between the expectation of fx and f of the expectation of x, right? Right. Okay, so see which one is bigger or not. Okay, so if you look at the definition of the convex function, right? So this is a kind of an expectation, right? Let's say if x1 and x2 are random variables, and let's say if there's a random variable can only take two values. One value is x1 and x2, because lambda is between 0 and 1, so we can view that as a probability, right? So this guy is what? Is an expectation of x, right? And this guy, because the combination is outside, right? So this guy can be viewed as an expectation of fx, right? Therefore, so which one's bigger? So this one is smaller, this one's bigger, right? Similarly, so we can basically say that, so this is something inside, this expectation is outside, right? So which one is bigger? So the expectation outside is bigger, right? Like this case, right? This one is bigger. Okay, in that case, so we say this one is bigger than or equal to that. Right, does that make sense? Okay, so again, so we need to see when that can equal, right? Equality can be tricky here. So let's say if fx is strictly convex, okay, which basically means that, there's only one point, that is the minimum, strictly convex, then the equality holds if, and equality basically means the basically means this, right? So x has only like 1 point distribution. Right? So this basically means like x is kind of like a direct delta, like Kronecker delta function, right? So this basically means that x has to equal to its expectation, okay, with probability 1. So otherwise, it will not hold, right? Because it's strictly convex, right? Or means x has to be a constant with probability 1. Does that make sense? Okay, so yeah, I will not prove that. So yeah, you can look at the book to how to prove it, and or I will upload. I have some notes to prove that. So the proof that should be relatively straightforward, right? So yeah, maybe if I ask you to prove that, how do you do that? Any idea? So basically, to prove something mathematically means that you want to use something you know already to prove something that you don't know, right? So here, what do you know? you only know one thing, which is fx is convex. So what is convex is given by this definition, right? Therefore, you need to use that to prove the result, okay? So here, as I said, right, so this is a particular case of the theorem, right? Which case? It's when the random variable has only two values, right? When the random variable has only two values, that's given. You know that already. So now you want to expand it to arbitrary number of values, a finite number of values, but they're discrete, right? So normally when you see this kind of thing, how do you prove it? You know something, equals to 2, that works, and then you want to expand it to more than 2.
Induction.
Exactly. You just use induction, right? So the proof is exactly using induction, okay? See whether you can, I'll upload the proof detail online, and you'll see how we can prove it. Yeah, so it's kind of too time consuming, so I'll just skip it. But it should be relatively straightforward by using induction. Okay, so next we're going to use it to prove something that we really care about, okay? So the first one is that we want to prove one important theorem here. So want to use that to improve some information inequality. Okay, so which is this inequality? So that we proved before, hopefully still remember. The relative entropy between Px and Qx, so that's bigger than or equal to 0. Okay, so we want to prove that, and obviously we let Px and Qx be two PMFs. Okay, then we can see that. Okay, and here the equality holds if and only if Px and Qx are equal for all x, right? So hopefully you still remember how we proved that before. So do you remember? Right, let me see whether I can find it or not. So how can I close this file? If I click close here, then the app is closed. Interesting. Yeah, let's see. When did we talk about that? Probably, let's see, lecture 6. Yeah, exactly here, right? So this is how we prove it before, right? How do we prove it? We use this property, right? 1 x minus 1 larger than or equal to log x. Okay, so this is purely the property, of this function, right? It's kind of the same thing, but now we're going to use, this function is a concave function now. Okay, so basically we're using the Jensen inequality to prove that here. Okay, so which is different compared to this approach. Okay, so you remember this, right? Yeah. So now let's see. We're going to use a different approach to prove it. Okay, so this is our lecture. Yeah, let's see how we can prove it using Jensen's inequality. Okay, so similar as before, so we need to define a set A that, so it's for all the x where Px is bigger than 0. Okay, the reason we need that is, we have a Q here, right? So that's how we create this inequality. One way to create this inequality, right? So that's be the support set of Px. Okay, so now let's start our derivation. So the relative entropy between P and Q, right, that equals to the summation of this guy. So this is the same as before, right? So there's nothing new here, right? But from the second step, there will be something new, right? So we're going to use the, the concave property of this guy. Okay. Yeah, in order to use that, we need to flip it. Okay, you'll see why we do that, right? So we need to take Qx in the upstairs and Px downstairs, right? The reason we use that is later on we're going to see that we need to cancel this guy, okay? So we use that in our previous proof. Okay, then we need to take a minus sign in front. Okay, or let's move the minus sign here. Okay, and then so we have, let's view that as our function fx. Okay, and now of course this x and this x is not the same, right? So yeah, I'll just say, how about, that's our fx, but the function is as follows. Okay, the function, let's denote this guy as, for example, y, right? And then we want to study this function fy or equals to minus log y, right? So that's our function. Okay, here log, it just means log, right? It's easier to write this. Okay, so minus log y is concave. Okay, because minus log y is convex, right? Because log y is concave. Okay, and then we will just use the Jensen's inequality, right? What Jensen's inequality told you that, okay, this is bigger than or equal to that when the function is convex, and now it's reversed if the function is concave. Okay, but now we know minus log is convex, then therefore the expectation is bigger than or equal to f of the expectation. Okay, and from here we can see, so because we're thinking f as this guy, right? So basically that's the expectation of the function. Okay, so that will be bigger than or equal to the function of the expectation, right? So it's a log minus log, and use black. Okay, so that's bigger than or equal to minus the function, which is minus log of expectation, right? Expectation is px multiply the expectation what inside is this guy, right? So that's our variable. Okay, so that's a function of expectation. Okay, sum. Miss that. Okay, and clearly from here we can see, so this guy and this guy can be cancelled, right? That's why I flip the order here. Okay, and then so that's minus log sum over all x and the qx. Okay, and because x is a support, A is a support set of px, right? And so this guy would be less than or equal to this guy qx, right? And this guy is equal to 1, right? And therefore, so we can conclude that let's just write it here directly. So this guy basically is maybe let's write one more step here. So then this guy would be bigger than or equal to minus log x in x qx. So that is equal to 0. Okay, and then we'll finish our proof, right? We'll prove our relative entropy is bigger than or equal to proof, right? Any questions? This is kind of important, right? So we're going to use Jensen's inequality a lot, right? So here is a very clear way to use Jensen's inequality, kind of important, right? So if this is fine for you, then we need to be careful on two important position here, right? So one, normally in information theoretic proof, we need to be really pay a lot of attention every time we use inequality. Okay, so here we use an inequality here. Okay, and then we use an inequality here. Okay, so we need to be really careful to see when the inequality becomes equality. Okay, that's how we understand things, right? So so when this equality will hold for this step, so that's exactly Jensen, right? So when Jensen will hold, right? So this equality holds if and only if when this variable is a constant, right? That does not change, right? Remember? So for Jensen, so equality holds if and only if when x is a constant, okay? And here it basically means that qx over px if and only if this guy is a constant. Okay. Right, from here, so we can get, so qx basically equals to c times px. Right? Okay, so that's one place. And the other place holds with equality, we use inequalities here, right? So when this equality will hold, okay, so this equality holds if and only if what? Right, so this equality because of the because of this, right? Because here we have x in A and here we have x in x. Okay? And the size of A and the size of x are different. Right? So this holds when these two are equal, then it will hold. Right? So this holds if and only if the sum over x in A qx equals to the sum over this. So I say something wrong, right? So it doesn't mean that size of A and size of x are the same, but it basically means that, for the difference, for something that is in A but not for something that is in x and that's not in A, the probability of that with respect to q will be equal to 0. Okay, so we know this has to be equal and equals to 1. Okay, so we say that is 2, and from 1 and 2, right? Then we can conclude that. So the summation of qx for all the x, right, so will equal to summation of x for c times px, right? And clearly, so this guy has to be equal to 1, and we know that summation of this guy is 1, right? So since, and then we know that c has to be equal to 1. Okay, and then we're done. Right, does that make sense?
For the top inequality, what's supposed to be on the left-hand side of that? Is that
Oh, minus log and the sum over x in calligraphic x and overall q.
Yeah, but what's supposed to be on the left side of that?
What's specific on the left side? This one?
Yeah.
Bigger than or equal to?
No, what is it supposed to be compared to?
Oh, yeah, so this one.
Okay.
Yeah, just continue writing this inequality. Yeah, so basically, it's this guy, right? Inside is, so this guy is less than or equal to this guy, right? But because it's a decreasing function, right? And then therefore, the whole thing would be bigger than or equal to this guy, right? Is that clear? Yeah, then we'll finish the proof, right? Okay, so we're done for the proof. Oh, so we're over time. Okay, then we're going to continue. So next topic is that we're going to use this one to prove something else. Okay, great. Thank you.